For months, aircraft and ships across parts of Europe had been reporting the same unsettling pattern: GPS positions that drifted, jumped, or vanished entirely, with no clear origin. Ground-based jammers were the usual suspect, but the geography of this particular interference didn't fit the explanation. It was too widespread, too consistent, and moved in ways no fixed ground transmitter could produce. Two researchers at the University of Texas at Austin Radio Aviation Laboratory, Professor Todd Humphreys and doctoral researcher Zach Clements set out to find the actual source. What they found was quite literally in the sky. Most documented GNSS interference, including the widespread jamming we have discussed elsewhere affecting the Baltic and the Middle East, originates from ground-based transmitters, powerful but geographically fixed, and therefore identifiable through triangulation from multiple ground stations. This case behaved differently. The interference pattern was consistent, with a source moving through space rather than sitting on the ground, a possibility that immediately makes detection and attribution both technically harder and from a security standpoint considerably more serious. Locating a source of interference broadcasting from orbit requires a fundamentally different toolkit than locating one on the ground. Researchers correlate interference timing and signal strength across a distributed network of ground receiving stations, cross-reference that data against known satellite orbital positions and trajectories, and analyze the specific structure of the interfering signal itself for clues about its power source and antenna design. It is a painstaking process of elimination, closer on forensic reconstruction than a single dramatic discovery. Humphreys and Clements were able to detect, characterize, and ultimately identify a powerful space-based source responsible for the interference pattern disrupting GNSS reception across the region, publishing their full methodology and findings openly, specifically so the broader navigation security research community could apply the same detection techniques elsewhere. This is worth sitting with. The same rigor and openness that characterizes strong engineering research was applied directly to what is functionally a live infrastructure security threat, turning a diffuse, harder to pin down problem into a documented, characterized, and therefore addressable one. It is worth understanding the actual instrumentation behind work like this, because it illustrates how much of modern infrastructure security research depends on patient, distributed data collection rather than any single breakthrough sensor. Detecting and characterizing this kind of interference typically requires a network of specialized GNSS monitoring receivers capable of recording not just whether a signal is present, but its precise timing, power level, and structural fingerprint. The specific technical signature that can distinguish one interference source from another, cross-referencing the fingerprint against publicly available satellite orbital data and against the timing of reported interference events on the ground. It is what allows researchers to narrow an enormous three-dimensional search space down to a specific identifiable source. None of the individual techniques involved are exotic. What's exceptional is a discipline required to combine them into a conclusive result. The significance of this research extends well past resolving a single case. Prior to this kind of rigorous, publishable methodology, much of the public discussion around GNSS interference relied on second-hand reports, aggregated flight tracking anomalies, or classified assessments that couldn't be independently verified by broader research or aviation safety community. Academic work of this caliber changes that dynamic. It gives regulators, airlines, and infrastructure operators a peer-reviewed, replicable method for detecting and characterizing space-based interference themselves, rather than depending entirely on intelligence agencies to identify and confirm threat after the fact. That shift from reactive intelligence to proactive, independently verifiable detection is precisely the kind of resilience building response we've discussed in relation to other infrastructure vulnerabilities in this series. For aviation authorities, shipping operators, and telecommunications providers, the practical takeaway mirrors the broader resilience principle we kept returning to: build detection and verification capability that doesn't depend on the interference source cooperating or revealing itself voluntarily. Research of this kind is precisely what feeds into the assured positioning, navigation, and timing systems now being developed across the aviation and maritime sectors, systems designed to recognize when a signal is being manipulated rather than assuming every satellite signal received is automatically trustworthy. There is something genuinely assuring buried inside an otherwise unsettling story, a threat that once seemed diffuse and unreactable and untrackable. Interference appearing to come from now here, disrupting navigation across an entire region, turned out to be findable through nothing more exotic than careful measurement, patient cross-referencing, and rigorous scientific method. That is a useful reminder for how we should think about infrastructure security. Generally, the answer to an invisible threat is very often not a bigger countermeasure, but better instrumentation. Thank you so much for your presence, and I'm looking forward to see you in the next lecture.